Hi, welcome to chapter 2. Today we will talk about polar covalent bonds, acids and bases. Remember that these recorded lectures are not substitute to attend to the lectures. Okay? This is only a summary to help your study, but you have to attend the lecture, you have to read the books, etc. Today we will talk about polar covalent bonds and acids and bases. This is the different points that we cover. Polar covalent bonds, electronegativity, dipolar moments, formal charge, resonance, rules for resonance forms, growing resonance forms, acids and bases, the Bronsted-Lowry definition, acid and base strengths, predicting acid and base reactions with pK values, organic acids and organic base, acids and bases, the Lewis definition, non-covalent attractions between molecules. Okay? Basically, we will focus on chemical reactivity, bond polarity, acid-base behavior of molecules, and hydrogen bonding. On the other day, we was talking about covalent bonds. Okay, basically, we was talking about carbon-carbon bonds, carbon-hydrogen bonds. That means bonds that both atoms has a similar electronegativity. But what happens when we have a different electronegativity? For example, in the extreme case, we can have sodium chloride. Sodium chloride, when we form a bond between the sodium and the chloride is by far more electronegative than not the chloride, and it's taking the 2 electrons of the bond are taken by the chloride, and the sodium remains as a cation. That means we have anions, that is a chloride negative, and cations that are sodium positive. Okay, and this creates a network of ionic bonds. However, when we are talking about covalent bonds, remember that we are joining the both orbitals and we are creating a new bond, a new molecular orbital. But of course, if one of the atoms of the bond is more electronegative than the other, what could happen is that basically, for example, if we have a carbon and a chloride, the chloride is by far more electronegative than not the carbon, and then this bond, this molecular bond, is polarized. That means the chloride, because it's more electronegative, will attract more the electrons, as you can see here, will attract more the electrons close to the chloride, and we have a density negative charge close to the chloride and a density positive charge close to the carbon that is the more electron positive or less electron negative atom. Okay, this is the periodic table. Remember how works the electronegativity is increasing from left to right. Each time that we are going to the right is more electronegative, and is decreasing from up to down. That means that the most electronegative atom has to be the fluoride. Remember that the noble gases are not entering in this classification. Okay, and probably the most electron positive will be the group 1. How we can know if the covalent bond is polar or non-polar? Well, basically, what we have to check is the difference between electronegativity. If the difference of electronegativity between the 2 atoms is less than 0.5, means that it's non-polar. If it's more than 0.5, it's a polar covalent bond. Of course, if it's by higher more, like more than 2, then what we will have is an ionic bond. Okay? But how we represent and how is affecting this? Well, basically, if we imagine, for example, methanol, that is a molecule of CH3 bonded to our edge, okay, we know that oxygen is more electronegative than not the carbon. That means that the major part of the electrons will be close to the oxygen, and this will create a density negative charge on the oxygen and a density positive charge on the carbon. If we represent this with a line, we can draw an arrow from the density positive charge to the negative density charge, that this will be the dipolar moment. Okay, numbers are not important, as we are organic chemists, that means it's basically qualitative. But we will always have this line, this arrow, that indicates the dipolar moment of the molecule. If we have just the opposite, for example, we have methyl lithium. Lithium in this case is more electropositive than the carbon. That means that now the carbon will be density negative charge, while the lithium will be density positive charge. This time we will have the same line, okay, the same dipolar moment, but opposite, because remember, the dipolar moment is starting always from the positive charge, from the density positive charge, and going to the density negative charge. Okay? Normally we represent electron-rich volumes in red and electron-poor in blue. And the electrons are displaced in the direction of the arrow of the dipolar moment. Inductive effect is simply the sitting of electrons in a sigma bond in response to the electronegativity of nearby atoms. Basically, what we are doing is checking the inductive effect, that is depending on the electronegativity of each bond and how each atom attracts the electrons due his electronegativity. Normally molecules are polar. The major part of the molecules are polar, because if we have a heteroatom like nitrogen, oxygen, phosphorus will be all these atoms are electronegative, or even halogens that are all electronegative. Okay, and then what we calculate is the dipolar moment, that is this line that I showed you before. Of course, this has a number, and it's called mu. The dipolar moment is called mu in the Greek alphabet. Okay, this is the formula that you don't need to know, and the only that you need to know is that, for example, the total dipolar moment is the sum of all the dipoles that present the molecule. What means this? For example, if we have carbon dioxide is polar. Well, the carbon oxygen is polar. That means this will be electron positive, this will be electronegative. The carbon will be electropositive and the oxygen will be electronegative. But because the both forces are going in different directions, compensates, and the total molecule is not polar. Okay? Despite each bond will be polar, the sum of all the polarities of the molecule makes that this molecule is not polar. Methane, in the case of methane, is slightly different, because what we have is that in the case of methane, we don't have any polar bond. Okay? We consider that the carbon hydrogen is non-polar bond. Same for ethylene and same for benzene. In all these examples, the dipolar moment is 0, or well, because we don't have dipolar moments, polar bonds, or because the sum of all the polar bonds contrast each other, and we have 0. Okay, here is water. Water, you can see that we have a clear dipolar moment in this direction. Here we have methanol. We have a lot of electrons here. That means that we have a dipolar moment in this direction. Or ammonia, again, we have a pair of electrons here. That means that the dipolar moment will be in this direction. Always from the positive to the negative. In this case, from the atom to the electrons. Here we have different molecules with his dipole moment. Formal charges, as the name suggests, are a formalism and don't imply the presence of actual ionic charges in a molecule. That means, for example, we have this molecule. Okay, this is dimethyl sulfoxide. We can grow the dimethyl sulfoxide in this way: sulfur bond with a carbon, sulfur bond with a carbon, and sulfur bond with an oxygen. Okay, being the oxygen negative and the sulfur positive. But also, we can write it in this way as a double bond. That means formal charges are different growings that allow us to explain better a molecule. Okay, doesn't exist, but allow us to explain better the behavior of a molecule. For example, dimethyl sulfoxide, where this sulfur-oxygen bond is highly polarized, where the oxygen has a huge electronic density and the sulfur has by far less electronic density. And we can arrive to draw it like this or like a double bond. Both are acceptable. What are resonance? Resonance are different structures that we can grow that none of one exists. This structure doesn't exist, and only growing representation to explain how is a molecule. We can take a look, for example, in this acetate. Okay, this methyl acetate. Here we have a methyl. Okay, all these bonds are well defined, and then we have carbon-carbon bond, carbon double bond oxygen, and carbon single bond oxygen with the oxygen negative. This is acetate ion. But what we can do is we can, for example, we can move this negative charge, this pair of electrons, we can put in forming a double bond between the oxygen and the carbon, and in order to don't break the octet, this double bond, one pair of electrons of this double bond can go to the oxygen to form this other form, this molecule. This and this molecule are two resonance forms of the acetate. This exists not. This exists not. What is existing is an average of all the resonance forms. Okay? That means that what we saw in reality, the reality is an average of this resonance form plus this resonance form. Okay, here we can see the resonance hybrid. If we have a carbon double bond oxygen, normally these bonds are at 135. Carbon single bond oxygen, this bond is around 135 ppm. While a carbon double bond oxygen is a 120 pm. When we analyze this bond, what we saw is that CO is around 127 pm, more or less in the middle. What we saw, as I told you, is an average of both resonance forms. Normally we can do resonance form with the p and non-bonding valence electrons. That means in p systems, or double and triple bonds, and non-bonding electrons. For example, here we have benzene. We can move all the electrons. This pair of electrons can move here to form a double bond here. Then in order to don't break the octet, we can move this here. And to don't break the octet here, we can move this here, as I show you here. These are two resonance forms. This is true. This form exists and this form exists. No. What is existing is an average of both. If we analyze all the bonds of benzene, we can see that all the lengths of all the carbon-carbon bonds are the same. That means we have a mixture between single and double bond in all the bonds of the benzene. Okay, the rules to form resonance forms are individual resonance forms are imaginary, not real, remember, are representations of the molecule to explain better his behavior. This is a clear example. Okay. Resonance form differs only in the placement of their p atoms, or their p electrons, double or triple bonds, and non-bonding electrons. Okay. Here you can see we can move these electrons to form these two resonance forms. The reality is the average of two resonance forms. Importantly, different resonance forms of a substance doesn't have to be equivalent. Here you have a very nice example that cannot be equivalent. Okay. If we have acetone and we at a base, we can deprotonate. We can remove one of these protons, forming a negative charge here. That can resonate. This negative charge can form a double bond between this carbon and this carbon, and then to don't break the octet, the carbon double bond oxygen, a pair of electrons has to go to the oxygen to form these resonance forms. These resonance forms are not equivalent, but both of them explain the behavior of the molecule. Okay, always the resonance hybrid is more stable than any individual resonance form. Of course, the average always will be more stable. Okay. Importantly, doing resonance forms, you cannot break the octet under any circumstance. Okay, don't break octets. Here is a clear example of a mistake that you can do. You have an acetate and then you put the pair of electrons in the oxygen to form a carbon double bond, to form this resonance form. These resonance forms could look correct, but it is not. Why? This carbon has 1, 2, 3, 4, 5 bonds. He's breaking the octet. How many orbitals has a carbon? Only 4. Is in the second row, only has accessible the 2s and the 2p. Total 4 orbitals, 1s, 3p. We cannot expand the octet. Basically, in general, any free atoms grouping with a p orbital on each atom has two resonance forms. This is a clear example. As you can see here, we can move the different resonance forms. Here, if we make a negative charge here, we can put the negative charge, making a double bond here, and then we have to move this pair of electrons of the carbon double bond oxygen to the oxygen to form this resonance form, and we can do just the opposite on the other side. Okay? please do this exercise at home. I imagine that we have this compound. Okay, we have a benzene, and we add an alkoxide. We can do the resonance form. We can put this negative charge forming a carbon double bond oxygen, and then we have to move this double bond to form a negative charge in this carbon. An important trick or tip to do resonance forms is that if in the starting form we have a negative charge or a positive charge, whatever, we preserve the charge in all the resonance forms. That means if we start with charge, in this case minus, in all the resonance forms we will have a minus charge. If in some moment you lost the charge, or you have two negative charge, or you have two positive charge, you are doing something wrong. Please revisit. Okay, acids and bases. The Bronsted-Lowry definition. This is the basic definition of acid and base. And basically a Bronsted acid is a substance that donates a hydrogen bond, a hydrogen ion, H+, and a Bronsted base is the substance that receives or accepts a hydrogen ion, H+. Okay, for example, here we have different acids. We have hydrochloric acid plus water. Hydrochloric acid will lose this hydrogen, okay, forming the chloride, while the proton that generates the hydrochloric acid can be taken by the oxygen to form the conjugate acid. This is acid base. Basically, acid is a compound that gives a proton, base is a compound that receives the proton. Here you have the acetic acid. We can have acetic acid. Acetic acid gives a proton, and a base, for example hydroxide, will take the proton to form the conjugate base, acetate, and the conjugate acid, in this case water. Ammonia, exactly the same. Ammonia is a base. Why? Because we have a pair of electrons that can accept a proton. For example, we add water. Okay, water can lose this proton and give this proton to the ammonia to form hydroxide and the conjugate acid, that is the ammonium salt, the ammonium cation. Okay. The strength of the acid of base is depending on its nature, but for example stronger acids like the HCl, that I am sure that you saw it, react almost completely with water. That means hydrochloric acid releases the proton at full, while weak acids, like could be acetic acid or other organic acids, only react a part of the acid. Okay, this is controlled by equation. Okay, here it is, acid plus water, conjugate acid, conjugate base plus conjugate acid. If we define the equilibrium of this reaction, what we have is the Ka, the constant of the acidity reaction, is depending of the concentration of the products divided by the concentration of the starting materials. In this case, because water is the solvent, I didn't consider in the equation. It's a constant that I can put in the K. The acidity constant is something not well used in chemistry, and what we use is normally the pK. And what is the pK? Is basically the minus logarithm of the Ka, of the constant acid. That means when stronger is an acid, When more conversion we have, higher is this number, because the pKa is minus logarithm of this number, smaller will be the pKa. And when a weaker acid is, bigger will be the pKa. Okay, here you have some examples where you can see the pKa of different acids. Remember, when lower is the pKa, higher the acidity. When larger is the pKa, weaker is the acid. Thanks to the pKa, we can calculate very fast if one acid is stronger than the other. That means, for example, we have acetic acid plus hydroxide will give us acetate plus water. We know that the pKa of the water is around 15, while the pKa of the acetic acid is around 4. Which is the stronger acid? Acetic acid. That means that this equilibria will be going to the products. Why? Because the stronger acid is in this part. This has more tendency to give the proton and get the products. Okay. In the organic acid, we have several organic acids like methanol, that the pKa is around 15. We have acetic acid, that the pKa is around 4. And we have, for example, acetone, that the pKa is around 20. Okay, that means this is the most acidic, this is the second most acidic, this is the least acidic. Okay. All biological reactions normally involve organic acids and organic bases. For example, the reprotonation of methanol, or the reprotonation of acetic acid, or the reprotonation of acetone. Compounds like carboxylic acid, which contain the CO2H group, occurs abundantly in all living organisms. This is a typical reaction with acetic acid. We react acetic acid with pyruvic acid, and what we get is this compound. Organic bases are also common. For example, we have the methylamine, methanol, or acetone. All are or can be organic bases. The most common are the nitrogen organic compounds like methylamine, because remember that the nitrogen has the pair of electrons in the nitrogen that can take a proton. Okay, and also we have amino acids that combine acid moiety, like the carboxylic acid, plus an amino that is a base. Okay, normally these compounds are not in this form, are in his zwitterionic form. That means that the nitrogen is protonated and the carboxylic acid is deprotonated. What is Lewis acid and Lewis bases? Well, Lewis acid is a substance that accepts an electron pair. While a Lewis base, is a substance that donates an electron pair. What means? A Lewis acid will be something that has an empty orbital. Typical example, boron compound. Boron, okay, Bf3 is a boron bonded to 3 fluorides. That means that we are using free orbitals, and we have a free orbital that is free, that doesn't contain any electron. Okay, while Lewis base is a compound that contains a full orbital, an orbital with 2 electrons. Another example, we have a magnesium 2 plus, okay, is a Lewis acid. Why? Because we have the orbitals of the magnesium empty, because we lost the 2 electrons. And this can react with a Lewis base, for example this phosphate, to form this acid-base complex. Okay. Here is the example of the boron trifluoride. Boron trifluoride, the boron is in the second row, that means that has 4 orbitals available, but here, as you can see, we are only occupying 3 with the free fluorides. Remember that boron is in the third group, that means that only have 3 electrons around, that means that we have a free orbital in the boron. This free orbital of the boron can react, for example, with one of the full orbitals of the oxygen of this dimethyl ether. This dimethyl ether, the oxygen has orbital, 2 orbitals in the oxygen that are full of electrons. And we can generate this acid-base complex. Okay, normally, in order to grow Lewis acids and Lewis bases, what we are using is curved arrows, okay, where the pair of electrons of the Lewis base is going to the atom that has the free orbital, as you can see here. These will be used in the future to grow reaction mechanisms. Okay, some Lewis acids you can see here. Basically, anything that is a bronzed acid will be also a Lewis acid. That means the formation of protons. A proton basically is a hydrogen that has a free orbital. The s orbital of the hydrogen is empty because we don't have any electron. We lost the electron. Cations, basically a lithium plus, magnesium 2 plus, all of these are Lewis acid because we have the orbitals empty because we lost the electrons. And some metal compounds like aluminum trichloride, titanium tetrachloride, iron trichloride, zinc chloride, that basically we have free d orbitals that can be used. In some cases we have d orbitals that we can use as a Lewis acid, or in the case of aluminum, because it's from the group 3, the same than boron also has a free orbital. Okay, it's the same example than the boron. Lewis base normally is an atom with a pair of electrons, and basically is oxygen compounds, nitrogen compounds, sulfur compounds. Okay, here you have a lot of them, like methanol, ethanol, ethers, aldehydes, ketones, aminos, etc. Okay, all of these, any atom that has a pair of electrons, non-bonding electrons, will be a Lewis base. Okay, when we say this, we can talk about the non-covalent interactions between molecules. What means non-covalent interaction between molecules? Okay. When we have a molecule, we know that the molecule is what it is, for example, methanol, because we have a bond between the carbon and the hydrogens, and the carbon and the oxygen, isn't it? And this defines the molecule. But which is the interaction between molecules? That means how interact one molecule of methanol with another molecule of methanol. Basically, we can define the non-covalent interactions between molecules of 4 different types. One is what we will name the van der Waals forces, London forces or non-covalent interactions. That means any compound, for example an alkane, for example pentane, okay, has a cloth of electrons around, isn't it, for the orbitals. In this case, some dipolar moments can be induced. What means this? Well, if we have the electrons around the space around the molecule, isn't it? What could happen is, by luck, by possibility, we have more electrons in one part than in another, and then we create a small dipole. It's not that this dipole exists always, no, it's simply because at this moment two electrons were very close one to the other, and then we create a small dipole. This induced dipoles creates a attraction between the molecules. Of course, if we have a negative dipole and a positive dipole, these will be attracted. These are the van der Waals forces. That is, when we don't have anything, we only have bonds that are apolar, okay, and it's the weaker force. If we increase the electronegativity between atoms, what we can have is dipole-dipole forces, okay? Molecules are polar, for example, for example, ether, diethyl ether is polar. We have an oxygen negative who has a density, electronic density, negative electronic density, and a carbon that have a positive electronic density. Okay, we have a dipole. Of course, when two molecules of the ethyl ether are interacting one to the other, they can be close, the negative part of the dipole with the positive part of the dipole of another molecule, and we create an attraction between molecules. This will be the second strongest force between molecules. Finally, what we can have is a hydrogen bond. Okay, a hydrogen bond is when we have a hydrogen bonded to a heteroatom, oxygen or nitrogen or sulfur. When this is happening, basically this hydrogen can interact, as you can see here, with another electronegative atom, creating a hydrogen bonding network. That means the hydrogen is from this molecule but also interacts with the other electronegative atom. This is the strongest force. Okay? The next strongest force will be the ionic atoms, okay? But normally the organic compounds are not ionic. That means in organic chemistry we have the dispersion forces or van der Waals forces or non-covalent interactions that are temporarily repulsed in non-polar molecules, that is the weaker forces. Dipole-dipole, that is when we have a dipole, this will be the second force in importance. And finally hydrogen bonding, that is the strongest forces. What means stronger forces? Means that in this type of molecules, when we have a stronger intermolecular forces, our melting point and boiling points will be higher, okay, because the molecules will be more attracted one to the other. A typical example of the importance of, for example, hydrogen bonding is in the DNA. Okay, in the DNA, the helix of the DNA basically is formed by hydrogen bond interactions. Also, we have the hydrophilic and hydrophobic effects that are quite important in the quaternary structure of enzymes and peptides. Okay, and that's all. Thank you very much for your attention, and see you soon.